que la interfaz sería eso.
Sí.
Y ya, o sea, antes de arrancar de manera efectiva un diplomado o estas cosas,
¿Nos escuchan?
tener una herramienta ya bien probada. O sea, yo creo que en cuanto se tenga las cuestiones técnicas más o menos claras, y ahora sí después de Semana Santa o algo así, en segundo semestre, o algo así, lanzas una compra y digo, tienes que hacer trámites con UNAM para que te den el certificado y eso, pero
Hola, Ensenada, ¿nos escuchan?
Can you hear me?
Yes.
Hola. Ay, no sé dónde estoy. Sí, ya lo sé.
Aquí estamos, si nos escuchan.
¿Nos escuchan, Ensenada? Sí.
Okay.
Bueno, vamos a empezar.
This is the light.
Okay, and can I also move the slide?
I don't know how to put the slide again because we turn off the wireless. better because if not,
Okay. Turn it off and well.
okay. Okay.
Okay, guys.
Well, we're back and light.
Fantastic. Thanks. Okay, so if there are no objections, I can start. Okay, so well, glad to see you back for the second lecture of this cycle devoted to understanding quasars as accreting black hole. Yesterday, we have reviewed a lot of correlations, and we have also said that this correlation can be basically associated with the so-called eigenvector 1, which is in turn defining a main sequence of quasars. Basically, by knowing the location of a quasar in the main sequence, thanks, of course, to the optical or UV spectrum, we can contextualize the properties of that individual quasar in a sequence of properties or in a sequence of trends that change in a systematic way along the main sequence. And let me recall briefly the main trends that we have considered, which are correlated to the main sequence. And also let me recall that if one considers two parts of the main sequence, one with full Vitas maximum of h beta less than 4,000 kilometers per second, and one above this limit, well, we see a sort of discontinuity in observational properties. And empirically, it has proved to be efficient to separate two populations. One, population A, which can be thought as an extension of the narrow line Seyfert-1 galaxies, of the narrow line Seyfert-1 nuclei, and a second one that involves sources which are broader than 4,000 kilometers per second. The limit, as we said yesterday, at 2,000 is basically unwarranted on the basis of the observational properties that we see change at around 4,000 kilometers per second in full Vitas maximum of h beta. So yesterday, we have considered the main sequence as defined in the plane full Vitas maximum of h beta versus a parameter giving the prominence of Fe2. But we have stressed that there are many important correlates, and in particular, we have shown the trend about the emission of carbon-4. We have shown the trend for the centroid at half maximum, which is a measurement of the line displacement from the rest frame of the quasar. And we have shown the trend also involving the equivalent width of carbon-4. We have seen trends involving important diagnostic ratios that we are going to discuss today, which are sensitive, for example, to physical parameters, and in this case, the carbon-3 over silicon-3 to electron density. There are other correlates, for example, the far infrared color, which is different for the different populations. And another important aspect is, for example, the optical variability that is much more pronounced in population B sources. And also the occurrence of radio loud systems is segregated in the sense that radio loud quasars seem to be much more frequent in population B than in population A. The converse is true for broad absorption line quasars. Broad absorption line quasar with extreme broad absorption line truth seems to be observable only in population A. While in population B, we observe narrower absorptions, much more closer to the rest frame. And, well, there is a word to define this kind of phenomenology, and it is the so-called mini broad absorption line quasar phenomenology. I'm going to show you an example maybe tomorrow, because the difference of the two broad absorption line system again points toward a sort of force, let's say in very general terms, that is causing some internal shift. For the moment, we have kept a very, very empirical attitude, so that we don't have provided very much of a physical explanation. We have given for granted sometime that the active nucleus is due to black hole plus accretion disk and plus torus system, but basically we don't have attempted yet to explain our result in physical terms. Before doing that, I think that it is important to consider also what is the eigenvector 2, and the eigenvector 2 is related to luminosity. So we are looking at the definition of luminosity effect that expedient to analyze for low ionization lines like H beta, Fe2, and for high ionization line in a separate fashion. So, well, in order to do this, we have to consider that there is a quasar luminosity evolution, and that in the nearby universe, we have a dearth of luminous quasars. Basically, luminous quasars with bolometric luminosity larger than 10 to the 47 were rare sources even at relatively high redshift. Still, well, if we consider the diagram in which we plot the absolute magnitude versus the redshift, we see that, well, here we have basically the location of the low redshift quasars, and we see that it is possible to define a sample of very, very high luminosity quasar with absolute magnitude around -29, -30, and at the same time going deep into apparent magnitude, we can define also a sample at roughly the same redshift, which is, however, at much lower luminosity. And comparing a sample of low luminosity and high luminosity at the same redshift is the best way to make a comparison if we want to seek true luminosity effect. So here we have an example of the profile of H beta that were observed for quasar of very high luminosity at intermediate redshift. And basically, what we see that the distinction between population A and population B is preserved in the sense that if we analyze the spectra, we can easily, by sight, from the profile of H beta, from the prominence of F2, isolate the classes of population A and population B in a way that is very similar to what has been done at low redshift. In the course of the class, I will provide you with an exercise so that you can try to identify the spectral type and the population of the AGN. So it will be fun, I believe. So you will realize also that the differences are really remarkable. So, and at high luminosity, we continue to see this difference, which is clearly not strongly related to luminosity, because we can classify in the same way the spectra of the quasars. So here we perform a systematic analysis of the function of luminosity of the quasar appearance. Here we have the profile of H beta, the spectral region of H beta. You can see the Fe2 emission and the helium-2 4686 and the oxygen-3 line. It seems, as I was saying, that really we have a different profile for the two populations, A and B. In population A, let me say, we have a Lorentzian-like profile, and instead in population B, we have the possibility to fit the H beta profile with two Gaussians, one that is almost unshifted, and the second one that is much broader. And as we were saying yesterday, it's probably a consequence of the stratification of physical properties that we observe, we derive within the emitting region. So, and apart from the profile of H beta, there is also an important trend in oxygen-3. You can see the trend seems to be present for both population A and population B. And we see that the equivalent width of oxygen-3 is apparently decreasing systematically with luminosity. It seems also that the oxygen-3, especially at very high luminosity, is becoming broader and also systematically more blue shifted. Here is not shown, the blue shift is not emphasized, but it is something that is detected even in the composite spectrum at high luminosity. So as we were saying yesterday, the oxygen-3 somehow, even if it's emitted in a different region, different physical condition in terms of density and ionization level, most probably farther out than where the carbon-4 emission behave in a very similar way to the one of carbon-4. This is showing systematic blue shift with respect to the rest frame. Blue shifts that are dependent along on the position along the main sequence of quasars. So here the anti-correlation between equivalent width of oxygen-3 and the luminosity is indicated as a Baldwin effect. We will see later better what does it mean. Before going to higher ionization lines, it is important to stress a basic fact for low ionization lines. Here we see that as a function of luminosity, and here we have samples covering a huge range in luminosity, more than 5 orders of magnitude in bolometric luminosity. We see that basically, there are no strong trends in luminosities. If we consider the symmetry index, for example, of H beta, we consider the centroid shift at 3/4 and 1/4, we don't, even if we have a large sample, which includes almost 500 objects, we don't find anything significant. And you can see, well, that the distribution is really inconsistent with any significant increase or decrease as a function of luminosity. The only parameter that seems to have a slow increase with luminosity, the increase in this case is statistically significant, although very weak, is the full width maximum of H beta. And in my opinion, the description of this trend that we see in the full width maximum of H beta as a correlation with luminosity is a little bit misleading. It's misleading really because it is very weak. We observe a very large spread in full width maximum of H beta. In the low redshift sample seem to be even larger than in the high redshift sample of very high luminosity quasar, which are the red spots. So what does it mean? I think that a better interpretation is associated with what we expect from the virial relation and from the result concerning the size of the emitting region. Now, we are going to discuss better this relation, which is relating the full width maximum to the mass and to the distance, to the mass of the black hole and to the distance of the broadline emitting region. Basically, this is the virial theorem rewritten in the case in which all the gravitational field is concentrated in the mass of the black hole. So the full width maximum square is equal to a factor f, which depends on the geometry of the system, times, of course, the gravitational constant, times the mass of the black hole divided by the distance of the broadline region from the black hole. And we count on the fact that the distance of the black hole is dependent on the luminosity. And so we write RBLR proportional to L to the A, where A has a value of 0.5, around 0.5, 0.6. And even in this case, we can easily see that full width maximum can be rewritten in terms of a dependence on the Eddington ratio. By dividing above and below by luminosity, we obtain a term that is related to the luminosity to mass, which is proportional to the Eddington ratio. And we see that ultimately the full width maximum is, for a given Eddington ratio, proportional to the luminosity to the 1 minus A divided by 2. So, and in the case of A equals 0.5, the trend is with the luminosity at 1/4. So there is a weak dependence on the luminosity, and the full minimum, full width maximum, we can see it from here, is reached in the case of maximum Eddington ratio. So we have that the Eddington ratio increases and the full width maximum decreases. So the minimum is reached in the case of the maximum Eddington ratio. So if we assume that there is a limit around 1 for the Eddington ratio, we get a minimum full width maximum that is increasing with the luminosity to the 0.25. what does it mean? It means that if we assume that the broadening of the lines is due to Doppler effect because of orbital motion or motion around a massive black hole, and we assume that the size is proportional to the luminosity to the A, then we can reproduce very neatly the trend relating a minimum full Vitas maximum to the luminosity. And these assumptions, of course, of virial motions and of this dependence of the distance of the emitting region to the central black hole proportional to L to the A have to be verified observationally, and they have been, and they will be discussed a little bit later. So basically, now we can think about what is going on the high ionization line. On the high ionization line, we consider the carbon-4 1549, of course, as prototypical because it is shifted into the visual domain for intermediate redshift quasars, and we can compare. We can compare the profile of carbon-4 to the profile of H-beta. As done for the low redshift sample, we overlay here to the observed carbon-4 profile a scaled profile of H-beta. The H-beta profile is also reproduced here, and this is done for 3 population A sources and for 3 population B sources. So you can see that basically the carbon-4 profile is almost always showing a prominent blueward excess with respect to the H-beta line that is instead at a redshift consistent with the one of the rest frame of the quasar. So this is telling us a lot, because the two lines, well, don't seem to know very much about each other, because, well, the systematic shifts are very large. We are speaking about 5,000, 3,000 kilometers per second, and this is something that has been found in all samples at very high luminosity, all samples of quasars at very high luminosity, for which it was possible to compare in a meaningful way the H-beta profile and the carbon-4 profile. So, what is going on then with the main sequence at high luminosity? Well, we have seen that we have a trend not only for carbon-4 in terms of higher amplitude blue shift, but also for H-beta in terms of the full Vitas maximum. The full Vitas maximum in one of the 2 parameters that enters in the diagram defining the main sequence at low redshift. So at low redshift, we have a situation like this for the low redshift quasars, and we see that, as shown yesterday, the large blue shifts are confined in the extreme population A, and we see a trend of the blue shift amplitude of carbon-4. Basically, the main sequence at low redshift is traced here by the green path, and it is involving objects with full Vitas maximum H-beta is relatively low, which can reach around 1,000 kilometers per second. and so they appear in this lower part of the diagram. When we go at high redshift, basically, not only we see an increase of the blue shift amplitude, but what is most important, we find a consistent increase in the full width as maximum of H beta. Because now, unlike for low redshift quasar, for which we have a minimum luminosity of around 10 to the 44, now we have a minimum luminosity of around 10 to the 47. At this luminosity, very narrow profiles of H beta are not anymore possible. If the virial relation and the dependence of the RBLR on luminosity is, as we assume, well, if the virial relation is satisfied and the dependence of RBLR on luminosity is as we assume, then sources which would be here are not anymore possible at very high luminosity. And so what become impossible, for example, from this diagram, you can see narrow line Seifert 1. Narrow line Seifert 1 should not exist at very high luminosity if our assumptions, of course, are verified, which is for which we have a very good reason. And so, basically, of course, as telescope will become larger and the efficiency of the spectrograph will improve, we may sample also a range at low luminosity at very high redshift. In this case, well, we should find a narrow line Seifert 1. But as a matter of fact, they are forbidden at very high luminosity. So now let me focus on the behavior of carbon-4 and other higher ionization lines. We have seen an important effect of luminosity on the main sequence, that the main sequence is basically displaced toward a larger value of the full width as maximum H beta, because the virial relation and the relation luminosity size of the broadline region are both satisfied. Now, the importance of the trend of carbon-4 with luminosity are related to an important correlation that was found in the late 70s by Jack Baldwin, and it is the so-called Baldwin effect, which is an anti-correlation between the equivalent width of carbon-4 and the luminosity. The equivalent width dependent very strongly in the original correlation. This is the plot from the original paper of Baldwin, to the point that Baldwin and collaborator thought, okay, when we measure the equivalent width, we can derive the luminosity of the quasar, because here the correlation is apparently very strong, very well defined, very strong. And so the Baldwin effect, it's important also because it raised some cosmological expectation. So derive the luminosity of the quasar in a way that is independent on redshift. As data became available for a larger sample of quasars, here we have a plot of the equivalent width versus luminosity for a low redshift, mainly a low redshift sample, in which carbon-4 was observed with IUE, which is basically an ancestor of space telescope. And you can see that the dispersion was very, very high, and so that the correlation appeared already very weak, and so weak that cosmological inferences were already impossible. And also, here are not shown the position of narrow-line Seyfertman sources, which go in the sense that they widen even the spread of the correlation that, I say it again, is very, very weak. The correlation has been confirmed, however, by very, very large samples based on the SDSS involving thousands of quasars as very, very weak with a slope around minus 0.1. So you can see that the spread in the luminosity range where you have the best sampling is enormous. So it is not really something that can be used to infer the luminosity, because for similar equivalent width, you have basically more than 1 order of magnitude spread in luminosity. However, the Baldwin effect remains important because it's not connecting only the carbon-4, but it's connecting also other higher ionization lines. For example, the highest ionization lines, the oxygen-6, 1034, has a very steep slope of the Baldwin effect. And it was found that the slope of the Baldwin effect is dependent on the ionization potential of the ionic species from which the line originates. And that is very, very interesting, because this means that there could be some intrinsic effect related to luminosity that, however, is very, very difficult to consider for the carbon-4 line. Oops. Sorry. So, and things started to converge towards a better understanding once it was found that basically there is a much stronger dependence of the equivalent width of carbon-4 with the Eddington ratio. The Eddington ratio is, of course, proportional to the ratio between the luminosity and the mass of the black hole, because the Eddington luminosity is the mass of the black hole times a constant. So here everything is given in unit of L over m, but however it is proportional to the Eddington ratio, with the Eddington limit around 10 to the 4.5, so around here. So basically, you can see that the Eddington ratio is much more relevant for the equivalent width of the carbon-4 line. And if we separate the sources also in spectral type, we see that the spectral type of population A are basically the one having the equivalent width of carbon-4 that is lower and lower with respect to the population B spectral type. So the Baldwin effect in carbon-4, as a matter of fact, is a very, very weak result. And if we assume that there is an equivalent width dependence on Eddington ratio as found, as shown in the previous slide, then we can explain in a plane, a theoretical plane, luminosity and equivalent width of carbon-4, the Baldwin effect, even without assuming any intrinsic dependence on luminosity. Basically, the equivalent width of carbon-4 is here well connected to the Eddington ratio. So we, in the sense that the low Eddington ratio sources have the highest equivalent width. So here we have we can, in this plane equivalent width versus luminosity, define an area associated with the minimum black hole mass and the minimum luminosity, minimum Eddington ratios, which is giving also the minimum luminosity, maximum black hole mass and minimum Eddington ratio, which giving us a higher luminosity, but at the same equivalent width. And the same can be done for the maximum Eddington ratio that is giving the minimum equivalent width. If we do this exercise and we assume a uniform coverage in this area, well, we obtain a slope of the dependence on of equivalent width on luminosity that is very, very similar to the one that we observe. Even a stronger dependence is possible if we assume a flux limit or if we consider other selection or evolutionary effect. So basically, the Baldwin effect that is found now is something that is most likely not intrinsically related to luminosity. This is not all of the story. Not all of the story because in 2009, some people defined a new class of quasars, the so-called weak-lined quasars. They are apparently the source which shows the minimum equivalent width of carbon-4. So, what are these sources? At first, they appeared very, very enigmatic, and however, they can be understood considering the trend of the eigenvector 1 sequence and also the trends related to the equivalent width dependence on Eddington ratio. So basically, here we have an analysis of the location of the weak-lined quasar with equivalent width less than 10, which are very, very faint in carbon-4. And we see once we obtain the H-beta spectrum in the near infrared that they are all located in the region of population A. I would say the overwhelming majority, save one point, which is, however, probably bad data with carbon-4 heavily absorbed. So basically, all the sources which are represented here by stars, all weak-lined quasars, belong to population A. And we see here the comparison between a sample of extreme population A, the one with the strongest F2 around here, a sample of extreme population A, and samples of weak-lined quasars that have been studied by several people. And we see that there is a continuity between the extreme population A sources and the weak-lined quasar. The weak-lined quasar, of course, extend down to lower value of the carbon-4 equivalent width because they were selected by purpose with the condition carbon-4 equivalent width less than 10. But also the population A sources cluster in terms of equivalent width at around the limit of weak-lined quasars. So the two are intrinsically connected, and it is legitimate to say that weak-lined quasars are an extreme of the extreme population A sources. So at this point, we are in the condition even to reconsider a little bit better the Baldwin effect, because here we have a study involving several, tens of quasars, and here we see how the weak-lined quasars are located in the plane equivalent width versus luminosity here and Eddington ratio here. So we have said that there is a strong dependence on Eddington ratio for the equivalent weight of carbon-4. So to evaluate the true luminosity effect, what we have to do is to use samples in which the Eddington ratio is not changing very much. So all the weak-lined quasars are at a very high value of the Eddington ratio. And here we see that basically comparing lower redshift samples to the weak-lined quasars at very high luminosity, well, we see an important displacement, which can be considered a true Baldwin effect, because now we have eliminated, at least at zero order, the dependence on the Eddington ratio. So this is something that is important and is probably physically associated to the dependence of the maximum temperature of the accretion disk on the black hole mass. But we will see that about better later. And so the empirical result now is saying that we have a true luminosity dependence that was hinted at also by the luminosity dependence of the highest ionization lines that we found in the studies, for example, for oxygen 6, 1034. So let me summarize and give you a sort of take-home message. And during the first talk and during the first half of this now, we have spoken about the systematization of quasar observational properties. We have focused on the optical and UV spectrum because the optical and UV spectra are the backbone in the interpretation of quasar phenomenology. And we have said that, well, all quasar show basically the same lines, but not all quasar spectra are identical. And this is something very important because, well, considering all quasars identical in the spectra leads to misleading inferences, unclear inferences about their physical mechanism operating in them. And we have stressed that we have a very broad range in terms of ionic species emitting the lines in the optical and the UV. And that is very expedient to separate low ionization lines and high ionization lines, because they show really very, very different behaviors in terms of line shift and line profile, and so line width. Basically, we have stressed also that two correlation can be used to organize the quasar diversity. Quasar diversity for optical and UV properties, but also for multi-frequency properties. And probably the most important one in this sense is the eigenvector 1 set of correlation that allows the definition of a main sequence in which also we can define spectral type, and each spectral type is different from the other. We will see right afterwards an exercise in which you are asked to recognize the different spectral types, and you see that, well, the differences are significant. And then we have considered an analysis of luminosity effect, and the luminosity effect in the original principal component analysis were characterized as the eigenvectors 2. Let's say also that luminosity correlation in AGN are very dangerous. We have seen that the anti-correlation of the equivalent width of carbon-4 with luminosity is basically something that is not real. It's weak, and as many other correlations, it is exposed to a lot of selection effect. So this is the take-home message for the first part of the lecture. And now the next will be related to a summary of the foundation of the interpretation of the quasar spectra, and especially focused on the emission line spectra. And so I suggested that we take a break of a few minutes, and so I will continue afterward with the exercise. Be prepared and check again the slides and use notes. I'm kidding, of course. Okay, let's stop.
You can turn your microphone off.
How you
Here. You just turn this.
I cannot.
Maybe. ¿Alguien sabe? A ver.
I have no idea.
No. I have seen. I don't see.
Okay, can you hear me? And it's a nice way to start. And probably in the meantime, you have realized about the 7 small, not so small differences that you have to find between the spectra that are shown in the slide. And given the spectra, would you be able to identify the spectral type following what we have shown yesterday? That's Hector?
Yes, sure.
Okay, you can submit the answer in writing, if you prefer. So,
So what's the idea that we give you our opinion?
yes, so you see that there are several differences, more than 7 small differences, in each of the between the 3 spectra, and let me stress, for example, the one in the upper left corner is showing some emission of Fe2 surrounding H beta, is showing also oxygen 3 not very weak, and in the H beta profile we see a relatively broad wing extending to the red. And the spectrum below, has a strong oxygen 3. It has a very broad profile, almost absent Fe2, just a trace of Fe2, but basically almost nothing. And it is not that different from the spectrum above, but you can mind the difference. And the spectrum on the right instead is something that looks completely different, because you can see the extremely strong Fe2 emission, the much narrower and spiky H beta profile. Of course, you all know that the line over there is H beta, the broad line 1, and the oxygen 3 are on the right side of H beta. So the oxygen 3 basically disappears because most of the emission around H beta can be explained by Fe2 emission. So basically, then, if you want to make a suggestion about the spectral type, otherwise I can give you the solution. The solution on of this very simple question. Or maybe Edgar want to say something?
I guess that I can tell you that the image in the upper.
Sorry,
right.
the microphone is not working.
No? Yeah, it's working. Okay, sorry. The image in the upper right, I guess that it's AGN of population A, because I see the narrow broad line in H beta, and in the left is from the population B, because the profile of the broad emission line of H beta, it has a Gaussian profile. It's broader, and in the upper left, I guess that it's I don't know, in the region that it's the transition between population A and population B.
Well, yes, basically it is right. I think that
Also, in Ensenada can participate if you want.
sorry.
I was talking with Ensenada.
sorry. So, basically, Edgar was right, and of course, the left right is closer to population A than the lower right spectrum. However, a defining feature of the population B is present also in this spectrum. You see that we have a very extended red wing extending also below the oxygen tree. And the solution of the solution of the exercise is provided by looking at also the analysis of the line profiles. So we see that for the upper left spectrum, we have a red wing that cannot be explained by Fe2 emission underlying H beta. We always have some Fe2 emission underlying H beta, but that cannot account for the redwood profile of H beta. And in the spectrum on the upper right, we see that well, instead we have a very strong Fe2 emission that accounts for everything. No need to assume oxygen 3 emission. We have a regular Lorentzian profile plus a blue shifted component, which is associated to the higher ionization wind that we observe much better in the carbon-4 line. So basically, the solution is spectral type B1 for the upper left, spectral type A3, extreme population A, and spectral type B1++, which is among the broadest, which is including among the broadest sources which are detected, and the sources also that have a relatively weak, very weak, can be almost zero undetectable Fe2 emission. So, so you can see from the exercise that when we speak of different spectral type, we are speaking of objects which are substantially different. It is not simple, it is not simply a subtle difference that we are speaking about, but on the converse, the appearance and the strength of very important emission lines is basically different. So, and now let me go from the review of the systematization of the observational properties to some element of line formation. And this is a part that is not so easy if you don't have a notion of spectroscopy. I suppose most of you have read the Osterbrock and Verland textbook. No. Okay, and I have tried to condense the main concept of the textbook in a couple of slides. So I don't know if this attempt is successful, but I think that it is important to convey some basic concepts that are at the heart of the interpretation of the spectra. So let me recall what we are speaking about. We are speaking about in the basic of sources which have very strong emission lines. And well, we see that the spectrum in the optical and UV is so much different from the spectrum of creation galaxies that are characterized by well, by the sum of the stellar population, and they, as far as they are quiescent, they don't have emission lines, but instead the prominent absorption line, usually from unevolved stellar population. In the case, if the galaxy is the host galaxy of an AGN, and we want to make a very simple model, usually it is sufficient to consider the spectrum of a quiescent galaxy plus a population of stars which may have been formed more recently, which will give a somewhat different absorption line spectrum than this one. So we can recognize the evolved stellar population by the depth of the Calcium-2 lines in the near UV, and we can have some diagnostic from the G band at 4300 angstrom, and so that well, we can also, in the case of spectra in which the AGN is superimposed to a part of the host galaxy, which is the case for the wide majority of the SS spectra, then we can still recover some information about the stellar population of the host galaxies. But in the following, we will be mainly interested in the origin of the emission line. How are the emission lines that we observe in quasar formed, and what the physical factor makes them so broad, what the physical factor are behind the shift that we observe in the high ionization lines, and which physical factor is also behind the symmetric and apparently unshifted appearance of most lower ionization line. And so basically, let me remind that since, well, the discovery of quasar, basically, it is thought that the main mechanism for producing the emission line is due to photoionization by an ionizing continuum. An ionizing continuum which is usually defined by the continuum at energy above 13.6 electron volt, which is the threshold for photoionization of hydrogen. So we see that if we look at the UV spectrum, we see that the spectrum of quasars is continuing below this limit, and it is pretty strong. The early proof of photoionization, however, did not involve an observation, a direct observation of the ionizing continuum, which is extremely difficult to come by, and the data shown here were obtained by a space-based telescope, but instead, since many years, it was observed that the luminosity of the line, typically H beta, was proportional to the luminosity of the continuum, which is not the UV continuum, but the nearby optical continuum that was measured on the same spectra. So this is a strong indication that somehow there is a proportionality between the luminosity of the line and the luminosity of the continuum. So the continuum luminosity must be related to the production of the emission line. And in another word, we can say that the equivalent width of the line is constant, is not changing very much. We will see that this is not exactly true, but it was true at least in a first approximation with the data of many years ago. And another strong evidence that the mechanism for producing the emission line is photoionization, is that line respond to changes in the continuum. When the continuum increases, the line increases. When the continuum decreases, the line decreases. And this happens, however, with some delay, which is related to the distance of the continuum source to the emitting region of the lines. Basically, if we have the opportunity to observe an AGN and in the continuum an H beta over a relatively long period of time, we see that we obtain two light curves which are very similar to each other, but displaced in the sense that the curve associated with the line emission is, well, shifted in time by an amount which is around 20-30 days in this case. So from this, we will see, we derive a very good technique to estimate the distance of the emitting region from the continuum source. And so now, let me go to the main question. Why do we observe emission line? And to do this, we have to consider an atomic process, which is the so-called Rosland cycle, and which says that, okay, we have some initially a situation in which we have a UV photon above the photoionization threshold that frees an electron. Suppose this is the Grotrian diagram of an hydrogen atom. And then, following the photoionization, we will have that the electron comes back and goes down to ground state because of recombination. When it goes down to ground state, it can go down directly to the ground state, but can also recombine at excited level, giving rise to emission of a series of photons related to the jump from down to lower and lower atomic level. So basically, this process is clearly at the origin of emission of lines. So, but to understand why we get emission lines, we need to go a little bit further and to consider a continuum source that could be the accretion disk of, in general, also a star, and consider that the gas of the BLR or of any other emitting region is at a distance r. And we have that we can consider that the disk may subtend a solid angle that is provided by the area of the disk corrected by cos theta, which is a factor related to the inclination of the disk with respect to the direction of the line joining the broadline region and the center of the disk. So basically, the area subtended by the disk will be pi times the square of the diameter of the disk divided by 4 times the cosinus of theta. And the fraction of the solid angle that is subtended by the disk is given by the solid angle divided by 4 pi sterad, which is the solid angle of the sphere. So basically, we will have a dependence on this factor, which gives us how much the continuum is diluted with respect to a point that is lying over the disk. So we can also consider the that the energy density that will reach the broadline region gas will be the original density at the surface of the disk times the dilution factor, and it is basically equal to the flux divided by C. And the flux here is measured in erg per second per square centimeter. And the J nu is instead a measurement of the flux of the intensity per unit solid angle. And here we have assumed that there is isotropy, and we have put 4 pi times J nu as the flux that is reaching the broadline region from the accretion disk. So now we have to consider what is called the Rosseland cycle, and to consider that we have to again resort to a growth trend diagram in which we can see two processes which are possible both, and that are at the heart, however, of the production of emission lines. So basically we have a first cycle which involves, now we are considering no more a situation of photoionization, but it won't change anything if we were assuming that a photon is able to ionize, and then we have a recombination by cascade to down to lower and lower levels in the atoms. So basically, to keep things at the simplest level, in the simplest configuration, we consider 3-level atoms, and one process is the cycle A, in which we have a photon that is creating a jump from level 1 to level 3 of the electron in the ground state of hydrogen, for example. And then we will have that this electron can go down to the ground state after having been excited, passing through a transition from level 3 to 2, emitting one photon, and emitting a second photon from level 2 to level 1. And the cycle B is instead a situation in which we have excitement of the atoms by a photon that brings the electron to level 2, and then a second process of excitation that brings the electron to level 3. And then a possible outcome is the direct cascade to the fundamental level of the electron, emitting a photon that is with an energy that is the sum of the photons of the transition between level 2 and 3 and level 2 and 1. So basically, we have here a very general expression that is relating, going back to, cycle 1 specifically. We have a very general relation, however, that is valid in any situation in which we have excitation from ground level 1 to an upper level, and we have the number of upward transition is basically the product of the photon field energy density times the coefficient of Einstein, the big coefficient of Einstein for induced emission, and the density of the atoms that are in the ground state. Basically, what is giving the Einstein coefficient B is the Einstein coefficient B is giving us the probability per unit atom per unit energy density that a transition from one level to another one associated with the energy difference at in the spectrum of the radiation field is giving rise to excitation from one level to another. So this is a sort of probability of absorbing a photon for a given radiation field. And this term is very general. In atomic physics, we define basically the number of transitions in terms of a product. For example, if we think about recombination, here we have excitation, but for recombination, we will have something that is proportional to the number of electrons that are recombining times the number of atoms, ionic species, and by a coefficient that is giving us the probability of obtaining a positive outcome for either combination or collisional excitation. But this will be introduced a little bit later. The B1, which is the coefficient, a coefficient that is basically dependent, of course, on the U, but it is a sort of coefficient that is related to a sort of fundamental coefficient that is not dependent on the physical condition of the gas. It's simply related to an energy density that may have any spectral energy distribution that we want. So the B coefficient is a coefficient that is basically a universal coefficient, unlike other coefficients that we will define later. So basically what we have here now to consider as fundamental thing is the probability of having the various processes, and basically this is this expression applied to level 1 and 3 give us the number of transitions that we have originally from level 1 to level 3. Then we have to consider the probability of having a transition from level 3 to level 2. And that will be basically the fraction of the total, the fraction of the transition between level 3 and 2 with respect to the possible total transition. And here we have the A coefficient, which is giving us basically something that is proportional to the transition probability, and it is the Einstein coefficient for spontaneous emission. So here we have the probability of transition from 3 to 2, and then we have to define the probability of transition from level 2 to 1. And the probability will be the spontaneous decay coefficient divided by the spontaneous transition coefficient plus the emission coefficient and times the radiation density, which is defined by the dilution factor and by the product of the dilution factor and of the energy density of the radiation field at the surface of the emitter. So basically, when we consider transition from 2 to 1, we have that for the coefficient for spontaneous emission is giving the part that is going down from 2 to 1, and but this is only a fraction. Is a fraction of the total possibilities of transition, because the electron could be excited back also to level 3 by the absorption of a photons of energy corresponding to the difference between level 3 and level 2. So the number of cycle A is therefore this one, given by the number of transition from level 1 to 3, sorry, and by the probability that from the transition from 1 to 3, a cascade like the one depicted in the figure follows from 3 to 2 to 2 to 1. And this is the expression. But the important point is to consider that the process, cycle B, is much more unlikely. Why? So, because, well, first of all, the number of transition from 1 to 2, well, this is something that's relatively similar to the first term for cycle A. However, while the electron is excited at level 2, it has to absorb immediately a second photon that brings it from level 2 to level 3. And so basically, this term is much, much less in the case of a permitted transition than the spontaneous decay rate that is provided by the A Einstein coefficient that usually has very, very large value. So, and then we will have also the fraction of downward transition, which correspond to the electron going from level 3 to level 1. So basically, however, the key point is that it is very unlikely that a second photon is absorbed while the electron is in an excited state, because the spontaneous transition coefficient is extremely large, 10 to the 8 hertz, and this coefficient, if this is the point, is basically inversely proportional to the time spent by the electron in the excited state. So the electron in the excited state spend a very small time. And this is why this process, cycle B, is very unlikely. So that in equilibrium, in thermodynamics equilibrium, the two processes should occur with the same frequency. However, here we have a situation in which we don't have anymore the energy density of a black body or a stretched black body that is as large as we have it at the surface of the disk. We have an energy density that is lowered by a factor W, which is usually very, very small, so that we have that the probability of cycle B is lowered to, well, unlikely values with respect to cycle A. So this is the dilution of radiation that makes it possible that the cycle A producing emission line dominates over the cycle B, and this is true for emission lines produced in stars, for emission lines produced in AGN. The AGN continuum, basically in the ionizing continuum domain, is a stretched black body. So This is something very, very fundamental that is made possible by the distance of the emitting gas from the surface of the disk or from the surface of the star. And another interesting consideration that we can make in this context is to compute the luminosity of H beta. So, coming back to the line of H beta, we can consider a sort of definition of luminosity that basically the luminosity is the integral over a volume that we can think of a shell of radius r min to radius r max of the volume emissivity of the line, assuming here isotropic emission. Here we have H beta that is basically a JH beta that is basically the space emissivity per unit solid angle multiplied by 4pi, assuming isotropy. And so I think that then we can write the luminosity of the line as the energy of each photon times the recombination coefficient that is an effective recombination coefficient for H beta, and it is n times the number of protons and numbers of electrons that are available, let's say, for the production of the line. What does it mean, the recombination coefficient? It means simply that the number of transition, and this, as I was saying, is very general thing, that the number of transition giving rise to the lines will be proportional, of course, to the number of atoms available, to the number of electrons available, times a coefficient which is somehow giving the probability of the transition occurring and giving rise to a photon of H beta. And that is, of course, not a universal constant, need to be calculated from the physical condition, and is dependent relatively strongly on temperature and to a minor extent on density. So basically this is a formal expression, and however the recombination coefficients for H beta and also for the full recombination coefficient for the hydrogen atom. Oops. Okay. So, and the full recombination coefficient for the hydrogen species, well, are tabulated as a function of temperature, and as numerical values, they are basically, well, the H beta is about 10 to the 14 cubic centimeter per second. Here there is a typo, cubic centimeter per second, and the full recombination coefficient for the hydrogen species is a few 10 to the 13, with a small dependence on density and a stronger dependence on temperature. But what is the point here is that now we can link the number of ionizing photons written here as the luminosity from the threshold for ionization divided by the energy of the photons integrated over the frequency as basically the product of the number of protons times the number of electrons times the recombination coefficient integrated, of course, over all the volume that is the volume of interest. And so we can write the luminosity of H beta as basically the energy of each H beta photons times the ratio of the effective correlation coefficient of H beta and the total correlation coefficient for the hydrogen species, time the number of ionizing photons. So this basically is the fraction of ionizing photon giving rise to a photon of H beta. And we can define the equivalent width that we measure on the spectra as the ratio. Here it is written in an explicit form, but it's basically the ratio of the luminosity of the line divided by the continuum specific luminosity at a given wavelength. So we can rewrite the expression of the equivalent width in this form, and so we can transform the expression from the luminosity from unit wavelength to unit frequency, and we get this expression. We can rearrange the expression here to make it explicit in terms of the equivalent width. And so we have that equivalent width will be proportional to the luminosity, basically divided by the continuum. Here is written per unit frequency, but it's n times lambda squared divided by c, which is equivalent to the continuum per unit wavelength that divide the luminosity of H beta. So we can rearrange this expression by inserting the expression of the luminosity of H beta, and we can then derive here the expression before is repeated. We can now assume that the luminosity per unit frequency is described by a power law. We can then make it everything explicit in terms of the integral and the ratio per unit frequency of the continuum at some point that defines the power law. So if we assume a power law in the form of L equal L nu 0 times nu elevated to the minus a, then we get this integral, which we can compute rather simply, and we get an expression that is giving our equivalent width of H beta as a function of the ratio of the correlation coefficient, which is basically a constant for fixed temperature, of nu 0 and nu H beta to the minus a, which is known when we set a, lambda H beta divided by a. So we can simplify the expression and oops. And
I guess it's your computer because it says keynote.
oh, yes. Okay. So we are back to the expression of the equivalent width that is basically obtained in terms of a constant divided by a parameter a, which is the slope of the power law. And of course, the larger a is the fewer ionizing photons will be available. So basically for a parameter a equal 1, we may get an equivalent width of H beta, which is around 100 times the covering factor of the emitting region, which is the fraction of ionizing photon that really comes to the gas and is able to produce NH beta photons, NH beta photon. So covering factor is basically the fraction of the gas that is covering a sphere centered on the continuum source. So basically it is the solid angle subtended by the gas divided by 4 pi. So we have seen in this highly idealized case that the equivalent width of H beta is something that is predictable in the case of photoionization because it's basically proportional to the number of ionizing photons divided by the fraction of multiplied by the fraction of the photons that is able to produce an H beta photons times also the covering factor, which is related to the extension of the gas emitting being exposed to the continuum source. And this is highly idealized because the situation for quasar is more complex than simple recombination, and we have a very strong contribution of collisional ionization. And of course, one has to remember always that collisional excitation can produce emission lines, but that in quasars, at least, it is thought that the main ionization mechanism is photoionization, because it is thought that the electrons don't have sufficient energy to ionize the hydrogen and also the other elements. Now, let me go on with a third important aspect, and the important aspect is related to the collisional excitation of the lines. So we can write the luminosity of the line as we did before, basically by considering a line emissivity per unit volume. And we can consider, however, that in the realistic astrophysical situation in which we have a gas that is not rarefied, extremely rarefied, we have the possibility of excitation by collision with electrons predominantly. And here we can write, as we did before, basically the number of transitions that we expect as the product, of course, of electrons, of the density of electrons that are available for the excitation, the number density of the ionic species, let's be hydrogen or any other element is okay, times this coefficient that gives the probability of having a particular collision that is bringing our electron, for example, from the ground state to the first excited level. And this probability, of course, will be dependent strongly on the electron temperature with an exponential term and with also an inverse square root of the temperature term. And of course, it will be inversely proportional to the statistical weight of the lower level from which the collisional excitation occurs. So the rate of collisional excitation is expressed like the recombination coefficient in cubic centimeter per second. And if we want to keep things simple, we can consider a simple two-levels atom. And the two-level atoms is basically assumed to be affected by collisional excitation, bringing an electron from level 1 to level 2. And then from level 2, we have two possibilities. One is spontaneous decay, And the second one is collisional de-excitation. The spontaneous decay rate could be lowered by a factor beta, which is giving us the probability that the photon is actually escaping from the nebula and from the slab of gas that we are considering. So this expression is giving basically us the number of collision that is giving an excitation from the ground level to level 2. So then we can make explicit the level 2 in this expression, the number of atoms that have been excited to level 2. And we can consider also that the emission per unit volume associated with the collision will be basically given by this. The number of excited level times the probability that a photon is escaping from the nebula times its energy. So this is a very natural expression because it implies that once the electron has been excited collisionally, it decays radiatively to the ground state. And of course, beta is a probability that can be very low, can be 1 in the case of low density gas, but if the density of the gas is very high, then, well, the photon has a lower probability of escaping because it can be reabsorbed by another ions in the ground level. So basically, then can be also destroyed during more complicated excitation processes or by dust. And so, in the end, the photons that correspond to the transition from 2 to 1 is not able to escape from the nebula. So by rewriting the expression of N2 in terms of the excitation and probability and of the decay or collisional de-excitation, we get this expression. And this expression contains at the denominator the terms beta times the spontaneous transition coefficient and plus the electron density and the collisional de-excitation coefficient. So in the case we have very high density, the terms of the collisional de-excitation dominates. And at high density, the emissivity of the line becomes proportional to the density, and basically it is associated to a distribution, a population of the excited level that is corresponding to the Boltzmann distribution that we observe in thermodynamics equilibrium. And this is why the emission lines are said to be thermalized. And in this case also, we have an importance of the beta factor that could be relatively small because it is inversely proportional basically to the opacity of the lines, and the opacity of the line is expected to be very high because the density will be very high. So basically this expression tells us that the intensity of a line will grow very slowly with the density of the of the gas where the line is emitted. At the low density, on the converse, we will have basically that at every collisional excitation, photons will be emitted. So basically, the dependence will be with the square of the density and the inverse of the temperature and the exponential appearing in the collisional excitation rate. So basically, this means that when we get at very high density and the line is thermalized, we will see a growth of the line that is relatively much lower than with respect to the case of low density, when we see a growth of the line with density, with amount of gas, so that is proportional to the square of the density. So there exists also a critical value in which the two terms, the recombination one and the collisional excitation one, become comparable. And so from this, it is easy to, from the denominator here, it's easy to derive a condition for this critical density that is basically beta times the spontaneous emission coefficient of Einstein divided by the collisional excitation rate. And what does it mean? It means that if we have a permitted transition in which the spontaneous decay coefficient is very high, 10 to the 10, 10 to the 8, typically for the Lyman and Balmer series, then we will have a rate of collisional excitation that is around 10 to the minus 4, then 10 to the minus 6, then we will have basically a critical density that is extremely large. Instead, if we have a forbidden transition for which we have that the spontaneous decay coefficient is very low, say even of the order of unity in the most extreme case, we will have a very well-defined value of the critical density, and above this limit, the lines will be collisionally quenched because the collision will dominate. So basically, having in mind these three set of consideration, we can consider the explanation for why we have emission lines, which is related to the Rosseland cycle, in which the transition giving rise to emission lines by cascade are much more likely than the transition giving rise to emission by a sort of build-up of photons at excited levels, taking into account the effect that we can have from the ionizing continuum. The ionizing continuum is something that is able to reproduce the equivalent width of H beta to good accuracy, at least at some order of magnitude, but basically the values that are observed are the ones that we derived from the previous discussion. So, and the third element is about the role of collisional excitation. Collisional excitation is very important. It's very important. Why? Why? Because in the broad line of spectrum of quasar, we don't observe lines with low critical density. And so basically, forbidden transition in the ultraviolet spectra that have low critical density. Here, for example, the forbidden transition of carbon-3 corresponding to the transition from the term 3p2 to the term 1s0. That's a transition, a critical density around 8 times to the 10 to the 4 particles per cubic centimeter is not observed. Everything that is that has a critical density below 10 to the 9 is not observed. So we can infer just from this that the density of the broad line emitting gas must be very, very high. But then we can go a little bit beyond. Just with the things that we have said before, we can derive diagnostic ratios which are sensitive to the density and ionization parameter conditions that are typical of quasars. And the broad line emissions that is strongest in the UV spectra involve the carbon-4 line, the aluminum-3 lines, the silicon-4 line, as well as the semi-forbidden lines of carbon-3 and silicon-3. If you remember the UV spectrum that was shown yesterday, we have also trends in the relative strength of these lines, but basically these lines provide a useful diagnostic of the density and specifically of the density and other ratio involving other lines provide a diagnostic of the ionization condition of the line. And here basically in the following we can consider the carbon-4, aluminum-3 and silicon-4, which are all hydrogenic species, that is, they have only one electron in the external shell. And the transition giving rise to the line that 1549 for carbon-4 and the fundamental transition of silicon-4 around 1400, as well as the aluminum-3 transition, are all doublet corresponding to a resonance transition from the first excited level to the ground level. It is the case basically that we had considered before, showing the two level atoms, and can be interpreted with the help of this previous scheme. So there are other ionic species which are very much of interest in the ultraviolet, but I think that the most important ones are related to the emission of the line at 1892 and 1909 of carbon of silicon-3 and carbon-3, and in this case we have a semi-forbidden transition. Semi-forbidden transition means that the transition is basically not permitted according to the quantum mechanics selection rules, and that the coefficient for spontaneous decay is relatively small, so that there is a high probability that the lines are collisionally excited. They are very strongly sensitive on density, and in the case of these two lines, the density range is the one that is the one of the broadline region. We have 10 to the 9 for the carbon-3, and we have 10 to the 11 for the silicon-3 semi-forbidden transition. So basically, these lines, because of their properties as atomic, as emitted by particular atomic species, will give rise to ratios which are sensitive to the density in this domain. Of course, if the density were much higher, the two lines would become unobservable because they will be collisionally quenched with respect to the permitted lines that are still growing, are not thermalized, and are still growing with the square of the electron density. So basically, let me say, I'm going to conclude with the definition of several diagnostic parameters that are helpful in the interpretation of the quasar spectra. Basically, we can define them according to our need. So, for example, here we have two ratios which are related to the same ion, but in different ionization levels. So, here silicon 2 over silicon 3 lines, well, are a measurement of the degree of ionization of the gas that is emitting them. So, and then we have ratios that are sensitive to metallicity. For example, the helium-2 abundance is fixed because it does not change since the Big Bang, basically. So the carbon-4 over the carbon-4 line at 1549 over helium-2 at 1640 is a very good diagnostic of metallicity. Coming back to what we were saying before about collisional de-excitation, we can consider the pair of lines, aluminum 3 1860 divided by, and the silicon 3 1892, that provide a ratio that is sensitive to density, since silicon 3 has a very well-defined critical density. And the same can be said for the ratio silicon 3 over carbon 3. And other combination of ratios, combining different lines can be sensitive to a number of parameters. For example, the carbon-4 1549 and divided by the aluminum 3 is a ratio that is sensitive to the ionization level, but also dependent on the metallicity, because it involves, yes, ionic species with different ionization potential, but also different elements whose abundance could be different from the one that we want to assume. And so we have other values also that can be sensitive to metallicity. For example, the values of the ratio nitrogen 5 over carbon 4 over helium 2 1640. And to interpret, to properly understand these ratios, we need really the help of a photoionization code. What is a photoionization code? Is to predict somehow the statistical equilibrium of the level. So instead of having 1, 2, 3 levels, well, the computation are done for several, in the case of the most complex ionic species, for several tens of even hundreds of levels. For example, for iron 2, there are 370 levels that are considered in the calculation, considering all the possible radiative and collisional transition between the levels. So it is, in principle, something very simple, but in practice is tremendously complicated. And of course, you need to know the atomic constant and the transition coefficients, the recombination coefficient need also to be recalculated as a function of the physical condition, temperature, and density. And this is what a photoionization code makes. And with the photoionization codes, we are able basically to reproduce the population of the levels, and so to predict the transition that are coming from gas in particular physical conditions. So, and with the words of Ferland, Claudic is the photoionization code that is most widely used in the context of the Broadline region of AGN, models the ionization, chemical, and thermal state of material that may be exposed to an external radiation field or other sources of heating, and predicts observables such as emission and absorption spectra. In the case of quasars and the Broadline region, it is very helpful to relate the diagnostics that we have to particular conditions in ionization, metallicity, density, and column density. So to get the simulation started, we have to assume initially several physical parameters, typically gas density, and a parameter giving the photon, the quantity of photons, the number of photons that is reaching the emission line gas, and which is called the ionizing photon flux. One has to assume chemical abundance, a spectral energy distribution of the ionizing continuum, and also the column density of the emitting gas. And Cloudy is able to take into account all the radiative and collisional processes which are leading to excitation and the excitation of level and in the case of radiative process to the production of the photons that we see of the lines. So, well, let me conclude here. Just a few words of summary. Then tomorrow we will consider the main result that has been obtained from the application of Cloudy to the spectra of the broadline region. And let me say that we have started this section speaking about the luminosity effect on the quasar spectra, which we said are relatively minor, and to be detected need samples that cover a very broad range in luminosity. Then what we have done is to consider a little bit in a very simplified fashion the mechanism which are at the origin of the production of the emission line. And we have said that we have evidence for photoionization, and we have seen how basically photoionization and the effect of the dilution of radiation can lead to the production of emission line. We have seen how the equivalent width of H beta can be directly related to the ionizing continuum, and then we have considered a slightly more complex situation in which the gas is affected also by collisional processes. And we have seen that basically we can that collisional processes are very important when the density is relatively high, and density relatively high depends a little bit from the situation that we have, but it is high for some transition which are forbidden, for which the spontaneous transition probability, the A coefficient of Einstein is relatively low. So collisional process can lead to the suppression of the photons that would be otherwise emitted if the density had been much lower. So basically, we have seen that from the appearance of the spectrum that we don't see broad forbidden lines, so we can gain immediately an inference on the density of the emitting region that must be higher than the critical density of forbidden lines. We have seen a couple of them in the UV, but also in the opticals. For example, we don't have oxygen 3 that is emitted with a broad profile, and so we conclude that the density of the broadline region must be higher than the critical density of this forbidden transition. However, we observe in the spectrum, the UV spectrum of quasar, lines emitted by ionic species, which are mostly hydrogenic or with only one electron in the the external shell, and some of these ions have transition which are semi-forbidden, and this transition semi-forbidden, which correspond to an intercombination transition from usually from a triplet to a singlet system. The semi-forbidden transitions yield very, very strong emission lines, which are observed in the spectrum of quasar. So this provides, since they are so sensitive to the collisional process, a dialectic of density. We have defined also several ratios that can be helpful for the interpretation of the physical conditions. And we have said that for gaining information that is physically accurate, the interpretation of the spectrum needs the help of a photoionization code that is able to model the ionic species that are present in the gas with very high completeness, taking into account all the possible transition, radiative and collisional. I stop here, and tomorrow we will start to describe the result that we can obtain from the application of cloudy to the broad line spectra of quasars.
Okay, well, thank you, Paola. I guess, I don't know if you have any question, or I want you to remember that you can ask directly Paola, because some of you have asked me, but she's given the class. So please don't be shy. You can ask her. If not right now, you can look for her tomorrow in the morning or before class, whenever you want. And she's able.
Well, you can also leave a question in writing that I will try to answer right away. Read the theme and try to answer it right away.
Exactly. You can write down the question and you can give it to me or give it to Paola. Okay. I'll see you tomorrow. Thank you to you.
Alenka, ¿me escuchas? Creo que no me escucho.
No olviden anotarse en la lista.
Hola.
Porque no me voy a acordar quiénes vinieron y quiénes no. Entonces, para los que vean la firma es que vinieron y los que no,
Pero
pues...
no me escuchan.
Para lo de la constancia, a los quienes les interese.
Alenka. Hola.
Hola, ¿Ensenada?
Sí, me escuchas.
¿Tienen alguna pregunta?
Sí, yo tengo una preguntita, bueno, un par rapidito. Sí.
Okay.
Can we please ask her to go back to the exercise where the spectra that we need to identify the spectral type and the population? This slide? No, the slide with the exercise.
The slide with the
Spectra,
exercise.
the three spectra that we have to identify.
This one.
Yeah, because here we kind of agree with the answer you gave to her, but yeah, at the end we realized because we thought that the two on the upper side, on the top, we thought there were 8, particularly the one that is on the
They thought that this
left.
one was pop A.
Yeah. So my question is if there is a way to identify by eye, because the thing that confuses was the fact that we don't really see in the left, top left, we didn't really see the broad line, and in the one on the right, there are some lines that seem to be broad. So my question is if there is...
Between both lines.
Okay.
Yeah,
The name is Margarita.
Okay, Margarita, I think yes, you can distinguish the spectra by eye. Let's say that the B1 spectrum in the upper left part of the slide has some Fe2 emission, and also for oxygen 3 could be a population A object. However, by eye, you also see that H beta has a strong redward asymmetry that is extending below the oxygen 3, so it reaches a radial velocity on the red side that could be very well in excess of 15,000 kilometers per second. This feature